Chapter 3: Engineering Challenges of Anti-Gravity Vehicles. The dream of anti-gravity transport vehicles that float free of Earth's pull captivates the imagination. But turning this vision into reality demands engineering feats that push the limits of today's technology. This chapter explores the core challenges: crafting materials that can withstand the stresses of gravity manipulation, harnessing immense energy to defy gravity, designing control systems for three-dimensional navigation, and ensuring safety in a radically new paradigm. For engineers and innovators, these hurdles are not just obstacles, they're opportunities to redefine what's possible. Material science, building the unthinkable. Anti-gravity vehicles require materials that are lightweight yet robust, capable of enduring forces unlike any in conventional transport. Lightweight strength. To minimize energy demands, vehicles must be as light as possible while maintaining structural integrity. Carbon nanotubes, with tensile strengths up to 100 gigapascals, are a promising candidate, but their production is costly and limited to small scales. Graphene-based composites could also offer high strength-to-weight ratios, but scaling these materials for industrial use remains a challenge. Exotic material properties. Some anti-gravity theories suggest materials with negative mass or metamaterials that manipulate electromagnetic or gravitational fields. For instance, metamaterials with tailored refractive indices might redirect gravitational effects, but their synthesis is experimental and untested in real-world conditions. Environmental resilience. Operating in three-dimensional space exposes vehicles to variable conditions, temperature fluctuations, radiation, or even gravitational anomalies. Self-healing polymers or ceramics with adaptive properties could protect against wear, but integrating these into a cohesive design requires advances in nanotechnology and additive manufacturing. Why it matters. Materials define the feasibility of anti-gravity vehicles. Engineers must innovate to produce scalable, cost-effective solutions that balance weight, strength, and functionality, paving the way for practical prototypes. Energy needs, powering the impossible. Counteracting gravity demands continuous colossal energy far beyond what today's power sources can deliver. Energy scale. To lift a 1,000 kilograms vehicle against Earth's gravity, at least 9.8 kilowatts is needed just to hover, assuming perfect efficiency. Real-world systems with inefficiencies could require 10 to 100 times more power for sustained operation, especially during acceleration or maneuvering. Speculative power sources. Conventional batteries are inadequate. Fusion reactors, which could yield 10 mJ per kilogram, are a distant prospect, with ITER's first plasma not expected until 2035. Zero-point energy. Extracting power from quantum vacuum fluctuations is theoretically intriguing but lacks any practical framework for implementation. Energy storage and transfer. Ultracapacitors or superconducting. Magnetic energy storage could provide rapid bursts of power, but their capacity is limited. Wireless energy transfer, perhaps via resonant magnetic fields, might enable mid-flight recharging from ground-based stations, but scaling this technology to anti-gravity demands is uncharted territory. Why it matters. Energy is the bottleneck of anti-gravity transport. Innovators must explore radical solutions, compact fusion, advanced superconductors, or entirely new physics to make this technology viable. Control systems. Navigating a new dimension, moving freely in three-dimensional space, requires unprecedented precision and responsiveness in navigation and stability. 3D navigation. Unlike ground vehicles, anti-gravity systems operate without fixed paths, demanding real-time control of altitude, pitch, yaw, and roll. Advanced A, possibly, leveraging quantum computing, could process sensor data to adjust trajectories instantaneously, but such systems are computationally intensive and still in early development. Stability and balance. Maintaining equilibrium in a gravity-defying vehicle is complex. Magnetic field manipulators or high-precision gyroscopes could counteract wobbling, but their integration into a dynamic, lightweight system poses engineering challenges. Feedback loops must operate at millisecond scales to prevent oscillations. Traffic coordination. A fleet of anti-gravity vehicles would need a decentralized collision avoidance system. Blockchain-inspired networks or swarm intelligence could enable vehicles to communicate and adjust paths in real time, but ensuring reliability in dense urban environments requires robust cybersecurity and fault tolerance. Why it matters. Control systems are the brain of anti-gravity vehicles. Engineers must design solutions that combine cutting-edge computing, sensor technology, and network architecture to ensure seamless, safe operation. Safety protocols, protecting passengers and society A. Technology as disruptive as anti-gravity transport demands rigorous safety measures to mitigate risks. System redundancy. A power failure mid-flight could be catastrophic. Redundant energy systems, such as backup ultracapacitors or auxiliary thrusters, are essential. Emergency landing mechanisms, like deployable aerodynamic surfaces or parachutes, could provide fail-safes, but they add weight and complexity. Environmental impact. Hypothetical anti-gravity fields might interfere with atmospheric conditions, magnetic fields, or local ecosystems. For example, high-energy emissions could ionize air or disrupt weather patterns. Engineers must develop shielding or adaptive systems to minimize these effects, drawing on lessons from nuclear and aerospace safety protocols. Human factors. Passengers in 3D travel may experience motion sickness or disorientation. Cabins with artificial gravity or adaptive dampening could enhance comfort, but these add engineering complexity. Training operators to handle dynamic environments will also be critical. Why it matters. Safety is non-negotiable. Innovators must anticipate worst-case scenarios and design systems that protect users, bystanders, and the environment, ensuring public trust in this transformative technology. Conclusion. The engineering challenges of anti-gravity vehicles, materials, energy, control, and safety are formidable, but they echo the obstacles overcome in past breakthroughs, from the steam engine to the jet plane. For engineers and innovators, these hurdles are a call to action, to pioneer new materials, harness unimaginable energy, design intelligent systems, and prioritize safety. The path to anti-gravity transport is steep, but each solution brings us closer to a world where gravity is no longer a barrier, but a playground. Next steps. In Chapter 4, we'll explore the current state of research and development, spotlighting the labs, prototypes, and visionaries pushing anti-gravity closer to reality.